Good afternoon, lads and ladies. Today we're going to continue our talk about systems. First, I'm going to turn on my fan. It's getting a little cozy up here. Today, by talking about row reduction in matrices. So you probably noticed, as you worked through that last homework, that the process of solving a system, especially a larger system, like a 3x3 or a 4x4, is not very pleasant using elimination. It's certainly better than substitution, but without a good system, without a good specific technique for what order to do when, it can be a little bit tricky. So today, I'm going to show you a surefire way to solve any system. Today, we're going to learn row reduction in matrix form. So there's kind of two things to talk about. First, what is a matrix? And how is it connected to this idea of a system of equations? And then second, what does it mean to row reduce a matrix? Or more to equivalently row reduce a system. Definitions first. An M by N matrix is a rectangular array of numbers. With M rows and N columns. It looks like this. The entries you indicate with subscripts. So for example, a 2x2 matrix looks like, some people put them in brackets like this, A11, A12, A21, A22. So the numbers here are called entries. So the row 1, column 1 entry is called A11. Row 1, column 2 entry is called A12. Row 2, column 1 entry is called A21. And the row 2, column 2 entry is called A22. In general, Aij is the entry in row I and column J. An example of a 2x2 matrix, an explicit example, would be like 1, 3, 2, 7. We usually call these things by capital letters. So here, capital A is the whole matrix, and its entries are A11, which is 1, row 1, column 1. A12 is row 1, column 2, that's 3. A21, row 2, column 1, that's 2. And A22, row 2, column 2 is 7. So this is the matrix A. it looks like this. That's the actual matrix, and its entries we denote with these subscripts. A 3 by 3 looks like A11, A12, A13, A21, A22, A23, A31, A32, A33. And an explicit example here, maybe 1, 0, 1, 0, 2, 3, 1, 0, 7, something like this. And here, A11 is 1. A12 is 0. A13 is 1. A21 is 0. A22 is 2. A23 is 3. A31 is 1. A32 is 0. And A33 is 7. Matrices, it turns out, are the right vocabulary to talk about the system problem in. So if you want to solve a system of equations, no matter how big it is, the best way to do that is by converting it into a matrix. So these are what matrices are. Matrices are these rectangular arrays of numbers, right? Like this. This is a 3 by 3 matrix. This is a 2 by 2 matrix. And you can build a matrix of any size. It could be a 7 by 12 or a 2 by 5 or a 1 by 3. All of those are possible, but square matrices are the ones that we like to mess with most of the time, because those are the ones that correlate with systems which have unique solutions, or at least can have unique solutions. So I want to talk to you about how to take a system and put it into matrix form. And then I'm going to talk about what you can do to that system, or do to that matrix, to solve the corresponding system. I'll give just a second for those who are still writing, but then we're going to look at an explicit example or two where I take a system and put it in a matrix form. So when you look at a system of equations, you see something that kind of looks like these. And the trick for converting a system into a matrix is to just stop writing the variables. Let the physical location of the number tell you what variable it's attached to. Converting a system into a matrix. We're writing a system of linear equations in matrix form. Let me show you through an example before I give you the general case. Let me take the system, and I should grab a system who I know has a solution maybe. Nah, fuck it, not for the first one. Let's take 2x minus 3y plus z equals 0, x plus y equals 5, and let's do x plus 2y minus z equals 1. This is a 3 by 3 system. To put this into matrix form, you take just the numbers that are in front of each variable and you write those in a row. So this first equation here would tell me that the first row of my matrix is 2, -3, and then the number in front of this z here, remember if there's no coefficient written, that's just a 1. And then the second equation, x plus y equals 5, you can think of there as being a hidden 0z here. So he would be 1 from the x, 1 from the y, 0 from the z. And the third row would say 1, 2, -1. So this is what's called the coefficient matrix. It's the matrix, the rectangular array, made up of the coefficients from the system. If you look at this first column, the numbers in front of x, the coefficients are 2, 1, 1. And if you look at the first column here, the entries are 2, 1, 1. If you look at the middle column, the coefficients are -3, 1, 2. And if you look at the middle column here, that's -3, 1, 2. And the same is true of the last column, 1, 0, -1, 1, 0, -1. So this on its own is called the coefficient matrix. Then you put a dotted line here. You can make it a solid line if you want. And you put these numbers on the right. So 0, 5, and 1. This is called the augmented coefficient matrix for that system. The coefficient matrix on its own is just this stuff. And when you add on these right-hand sides, right, the right-hand side to each equation, here we call that augmenting the coefficient matrix. So that's called the augmented coefficient matrix. Here's the cool thing. All of the row operations that you can do to this system, like adding two equations to each other or multiplying an equation by a number, you can do to this matrix instead. And if you want to solve this system, the easiest way to do that is to get this matrix into what's called upper triangular form, where everything below the main diagonal is 0. The main diagonal is this, this, and this. I'm not going to go through and solve this system using this matrix because I just pulled it out of my ass and I have no guarantee that there is a nice solution. I just wanted to show you how to write down the coefficient matrix for a system. And then the move from here to solve the system we do what's called row reducing. We row reduce the augmented coefficient matrix until it is in what's called row echelon form. We'll just call it upper triangular form, or row. Your book calls it, this is the proper name, echelon form. What does that look like? You'd have something here, and then zeros beneath. And then 0 here, something here, 0 beneath. Actually, this guy up here doesn't have to be 0. He could be something else like C. And then something here. And then on the other side of your line, you'd have other stuff. Why is this nice? Well, because if you then rewrite this as a system, you'll be able to read off the solutions. First, you'd be able to say that like f times z equals I. So you can solve for z and then back substitute. When you write these things in the abstract like this, they look very intimidating. So I think the way to do this is going to be through examples. And I'm going to show you a notation that you can use for the row operations. The operations we use to get the matrix into this form, echelon form, row, echelon form, are one. You can multiply any row by a non-zero number. Two, you can add a multiple of one row to another row. And three, you can swap any two rows. You're going to use these three operations and follow a specific algorithm that I'm going to teach you today to take your arbitrary matrix, your whatever you started with, and get it into this form. Once you get it into this form, where everything below the main diagonals here are all zeros, then you'll be in a situation where you can read off the solution. All the hard work is going from this to this. The tools you will use are these three row operations, but you don't want to just try doing random row operations. You'll want to apply them according to the algorithm I will give you. So I'll leave here for just a second. All right, while you're writing, I'll dig us up a good example or two. All right. So let's get ourselves an example. You can add a multiple of one row to another row. That's this guy, yeah. Add multiple of one row to another row. And then the last one there is swap two rows. You can swap any two rows you want. Your goal, remember, is to get all of these things down here to be zeros. Once everything beneath this main diagonal are zeros, you win. So let me show you what this looks like. I'm going to go ahead now and begin with an actual example. I'll say computers are very good at this. Ray tracing, which if you're into gaming, you may have heard about, And most computer graphics things come from solving these big systems many, many times per second. So let's give a system. How about 4x plus 8y minus 4z equals 4? 4x plus 8y minus 4z equals 4. And then we can do 3x plus 8y plus 5z equals negative 11. And negative 2x plus y plus 12z equals negative 17. So we're going to solve this system by first rewriting it as a matrix, then row reducing that matrix, then converting back into a system, which will be easy to solve by back substitution because the system will be triangular, to use the language from last week's homework. So first, putting this into matrix form. My first row will be 4, 8, negative 4, and then on the far right over here will be a 4. I'll go ahead and put in my augment bar. My second row will be 3, 8, 5, negative 11. And my last row will be negative 2, 1, 12, negative 17. So this is the augmented coefficient matrix for that system. Compare the numbers. The column 1, all the things attached to x are 4, 3, negative 2. 4, 3, negative 2. 8, 8, 1. 8, 8, 1. Negative 4, 5, 12. Negative 4, 5, 12. 4, negative 11, negative 17. 4, negative 11, and negative 17. The algorithm you want to use is as follows. First, you want to make this entry a 1, however you can. Then, you want to make the entries below it a 0. Once you've done that, you want to make this guy a 1, and then make everything below it a 0. The entries along this main diagonal are called pivots. So pivot 1 is this position, pivot 2 is this position, pivot 3 is this position. Your first step is to make pivot 1 equal to 1. And looking at row 1, notice everything is divisible by 4. And if you divide this by 4, you'll get a 1. So my first row operation, and here's the notation, capital R1, this means new R1, is going to be what I get when I take old row 1 and I divide everything by 4. In other words, I'm going to multiply my row 1 by the constant 1/4. And I'll leave all the other rows alone. So this says new row 1 is equal to 1/4 times old row 1. That's what this notation is saying. New row 1 is equal to 1/4 times old row 1. So I'm multiplying through row 1 by the number 1/4. Rows 2 and 3 will not change, so I copy them down first. This is a really good habit to be in. Copy down the rows that you're not changing before you do anything else. Now, new row 1, the stuff that goes here is going to be all this stuff times 1/4. 1/4 times 4 is 1. 1/4 times 8 is 2. 1/4 times -4 is -1. 1/4 times 4 is +1. So this is what happens if you perform that row operation to this matrix. Remember the algorithm. First, make this a 1, then make everything beneath it a 0. So I've got this as a 1 now. I want to make both of these zeros. Of those 3 row operations, what can I do to make this in particular, a 0? Well, if I take this middle row and I change it by adding -3 times this first row to it, -3 times 1 is -3. When I add that here, I would get 0. So the row operation I'm going to do is my new row 2 will be -3 times my old row 1 plus my old row 2. That's the notation. So my new row 2 is going to be -3 times old row 1 plus old row 2. In other words, I'm going to subtract 3 of these from these. And when I do that, I will get a new matrix. I'm changing row 2. So rows 1 and row 3 stay the same. I copy them down first. So I've copied down rows 1 and 3. Now to get my new row 2, I take my row 1, old row 1, multiply by -3 and add. -3 times 1 is -3. -3 plus 3 is 0. 2 times -3 is -6. -6 plus 8 is 2. -1 times -3 is +3. +3 plus 5 is +8. -3 times +1 is -3. -3 plus -11 is -14. So here is the matrix that I get out. Now I've got a 1 in my first pivot. I've got a 0 below it. My next step is to get a 0 here. It's going to be this type of row operation again. I'm going to use this as my tool. I've got a 1 here. That makes this easy to use to kill things below. What do I need to add to this to make it 0? I need to add 2 to this. So if I multiply row 1 by 2 and then add it to this, this will go away. So the row I'm changing here is row 3. And row 3 is my new row 3 is going to be 2 times old row 1 plus my old row 3. I'm going to multiply this row by 2 and add it to this row. I'm changing row 3, so rows 1 and 2 stay the same. I copy them down. Now when it comes to row 3, I'm adding 2 times row 1 to row 3. So 2 times 1 is 2. 2 plus -2 is 0. That's by design. 2 times 2 is 4. 4 plus 1 is 5. 2 times -1 is -2. -2 plus 12 is +10. And 2 times 1 is 2. 2 plus -17 is -15. And I hope that you're seeing that none of these individual steps is all that hard, but there's a lot of place to make little fucking mistakes. And one little fucking mistake anywhere ruins the whole thing. So you need to go very slowly. Slower than I'm doing here, at least on your first example. And please, please always write this shit. Tell me what row operation you're doing. Write down the row operation that you're doing in case you forget while you're doing one of these little fiddly calculations, because there's so many little fiddly calculations where you can make a mistake. Let the paper be your memory. If you try to keep it all in your head, you'll make mistakes, I promise you. Remember what your goal was. Your goal, when we started here, was to make this a 1 and then make everything beneath it zeros. We want to get this into this form. Yep. Yeah, these steps every time will work. Our next move is to make this a 1 so that I can use him as a weapon to clear out the stuff below. And conveniently, everything here is divisible by 2. So from here, my new row 2 will be 1/2 times my old row 2. I'm going to get a 1 in the second pivot. So row 2 is the row that's changing. All the others will stay the same. I have 1, 2, -1, 1. That's row 1. And row 3 I'll copy down also because it's not changing. That's 0, 5, 10, -15. Row 2 is the one I'm modifying. I'm multiplying every element of row 2 by 1/2. 0 times 1/2 is 0. 2 times 1/2 is 1. 8 times 1/2 is 4. -14 times 1/2 is -7. So here's the resulting matrix. All right. I have a 1 in my first pivot, zeros below. I have a 1 in my second pivot. I need to make this a 0. I'm going to move this paper up because it's kind of dangling off my dot cam. So I'll give you a second here to copy in case you're still writing anything. Moving up now. Okay, 1, 0's beneath, 1, I need a 0 beneath, so I need to kill this 5. So I'm going to multiply row 2 by -5 and add it to row 3. In other words, my new row 3 is going to be -2 times my old row 2 plus my old row 3. That's the row operation. Rows 1 and 2 don't change, so I copy them down. The nice thing about this stuff is that it's very mechanical. It's just step by step by step, very simple steps, but you just need to be a little bit careful. Oh, sorry, so it's -5 I needed here, right? This is why writing these row ops is so nice. I almost made a little mistake. Yeah, I said I was going to multiply row 2 by -2 and add it to row 3. That wouldn't give me a 0 here. It's -5. I need to multiply this by -5 and add. Okay. So 0 times -5 is 0. 0 plus 0 stays 0. That's why it's so important that we made this 0 before. Otherwise, when we go to kill this, I would be messing up this position. 1 times -5 is -5. -5 plus 5 is 0. 4 times -5 is -20. -20 plus +10 is -10. -7 times -5 is +35. Is that right? I think so. Yeah. +35 plus -15 is 35 minus 15 is 20. So here is my almost done matrix. In fact, from this point, we could now solve. But just for fun, I said I want to make all of these ones and everything beneath it zeros. Having zeros beneath is necessary. Having these as ones isn't necessary, it's just nice. So if I wanted to, I could say my new row 3 is going to be -1/10 my old row 3. That'll give me a 1 in that 3, 3 position here. Rows 1 and 2 don't change. $10 divided by -10 is 1. 20 divided by -10 is -2. And now that I'm in this reduced row echelon form, this upper triangular form where everything below the main diagonal is 0, now I go back to writing it as a system of equations. I come back out of matrix land, back into system land. This is x plus 2y minus z equals 1. The middle row here is 0x plus 1y plus 4z equals -7. And this last row, this is the money, 0x plus 0y plus z equals -2. What is so dope about this? Equation 3 says just z equals -2. So there's the z part of your solution. Back subbing this, into equation 2 gives, well, it's equation 2. Equation 2 says y plus 4z equals -7. So y plus 4 times -2 equals -7. That's y minus 14 equals -7. And then you add 14 to both sides and you get y equals -7 plus 14 is 7. There's the y part of your solution. And back subbing both of these, in equation 1, we get x plus 2 times y, well, y is 7, minus z, well, z is -2, equals 1. So what does that say? That says x plus 14 plus 2 equals 1.
Where did you get 14 from?
2 times 7. Right here. So I'm plugging into this equation, right? And I plug in 7 for y and -2 for z. So when I plug in a 7 for y here, I have 2 times 7, right? That's 14.
I'm meaning like on the second equation, whenever you're solving that, it should have been -8, not -14.
Yeah, what the hell? Sorry, my brain must have farted. That's going to hurt us here. So that's another teachable moment, right? A little mistake anywhere will destroy us. Yeah, this should be y minus 8 equals -7. Sorry. Thank you for correcting me just before it hurt us. So now we add the 8, right? And we'll get y equals 1. Thank you, thank you. So y is 1, z is -2. Now putting this back into equation 1, we get x plus 2 times 1 minus, what was z, -2 equals 1, which means x plus 2 plus 2 equals 1. So x plus 4 equals 1, which means x is -3. There we go. All right, so our solution is -3, 1, -2. The ordered triple, x, y, z. Yeah, thank you for catching me on that silly mistake. There's lots of room for those little silly mistakes here. But this algorithm always works. And this is called by a few different names. Some people call it Gaussian reduction. Some people call it Gauss-Jordan reduction. Some people just call it row reducing. I think row reducing is the easiest thing to call it. The game is to always try to get to that form where you've got zeros beneath the main diagonal, because then you'll always be able to read off the last variable. Like here, this just tells me z equals -2, and then back sub that in here to get y, and then back sub both of those up here to get x. And even if you had a bigger system, like a 10 by 10 system, if you get it into this form, then you'll be able to read off whatever the last variable is and back substitute that to get the last 2, and back substitute those to get the last 3, and so on. It's not a fun process, and if I'm honest, I'd say this is a process better suited for computers than human beings, because it's made up of a bunch of tiny calculations and there's not really any creativity in there. But this is how it's done. Any questions on the row operations? Any questions on the whole process? Row operations, row reducing, converting system into matrix or back substitution. Okay, let's try a more challenging example then. I'm going to work a problem now that has infinitely many solutions, a 3 by 3 with infinitely many solutions. Again, these are a little hard to generate from my head, so I'm going to borrow an example from your textbook. How's about? -3x minus 5y plus 36z equals 10. Negative x plus 0y plus 7z equals 5. And x plus y minus 10z equals negative 4. So I claim that this system has infinitely many solutions. And I'll show you how to detect that and how to solve and state those infinitely many solutions. First, we'll rewrite this as a matrix. So my first row is negative 3, negative 5, 36, 10. My next row is negative 1, 0, 7, 5. And my bottom row is 1, 1, negative 10, negative 4. The technical name for a system with infinitely many solutions is a dependent system. Because really, these three equations are not, the term is like algebraically, really linearly independent. Some combination of two of these equations will give you the third, if you hunt for it carefully enough. But the way to sort all of this out is to now row reduce this matrix. One way I can get happy up here, I can get a 1 in this pivot position, is by swapping row 3 with row 1. Let's do that. So I'm going to swap row 3 with row 1. So I'll now have 1, 1, negative 10, negative 4, negative 1, 0, 7, 5, and negative 3, negative 5, 36, 10. I just switch row 1 with row 3. That's all. That gives me a 1 in my first pivot position. So now I want to clear everything out beneath it. To clear this out, I can just add this row to this row, because negative 1 plus positive 1 is 0. So my next row operation, I would say that my new row 2 is old row 1 plus old row 2. And again, I'll copy the rows that don't change first. 1, 1, negative 10, negative 4, negative 3, negative 5, 36, 10. And then row 2, that's the row that's changing. I'm going to add old row 1 to old row 2. That's my new row 2. So 1 plus negative 1, that's 0. 1 plus 0, that's 1. Negative 10 plus 7 is negative 3. And negative 4 plus 5 is 1. Now I've got a 1 in my first pivot and a 0 directly below. Next, I need to make this 0. Best row op for that is to multiply row 1 by 3 and add it down here. So my new row 3 is my old row 3 times, or old row 1 times 3, or 3 times old row 1 plus old row 3. It's row 3 that's changing, so I copy the other two down first. 1, 1, -10, -4, 0, 1, -3, 1. And now I multiply this by 3 and add it to this. That will give me a 0 here. 3 times 1 is 1. 3 times 1 is 3. 3 plus -5 is -2. 3 times -10 is -30. -30 plus 36 is 6. 3 times -4 is -12. -12 plus 10 is -2. So that gets me here. And luckily, I already have a 1 in this second pivot. So I don't need to create a 1 here. There's already a 1 here. So my first move from here is to kill the 2 down here. I'm happy with column 1. Column 1 looks how I like it, 1, 0, 0. To get column 2 how I like it, I need a 1 here, that's already done, and a 0 beneath. To get that 0 beneath, my new row 3 will be 2 times old row 2 plus old row 3. Multiply row 2 by 2, add it to row 3. That will get rid of that. So rows 1 and 2 don't change. Row 3 though, 2 times 0 is 0, 0 plus 0 stays 0. 2 times 1 is 2, 2 plus -2 is 0. 2 times -3 is 2 times -3 is -6. -6 plus 6 is 0. And 2 times 1 is 2. 2 plus -2 is 0. Something weird has happened here. I got a row of all zeros. The fuck? Well, what this means is that this bottom equation, let's rewrite this as a system now. Remember, when we talked about how to tell you have infinitely many solutions last week, I said if you get something like 0 equals 0, a tautology, that tells you that you have infinitely many solutions. This bottom row says exactly that. So I've, from my first row, x plus y minus 10z is equal to -4. From my middle row, I have y minus 3z is equal to 1. And from my last row, I have, I'll write the zeros here, why not? My last row, I have 0x plus 0y plus 0z equals 0. Equation 3 is a tautology. Which means infinitely many solutions. That doesn't mean every ordered triple is a solution. It just means there are infinitely many ordered triples which solve. How do you handle this? Well, let z, some people would just say let z be a free variable. The notation your book uses says let z equal t, be a free parameter. And then you solve everything else in terms of that. So z is just equal to t. It's allowed to be whatever number you want. Then back subbing in equation 2, you get y minus 3t equals 1, which means y is equal to 1 plus 3t. And if you back sub both of these, so here's my solution for y. Into equation 1, then you get x plus y, which is 1 plus 3t, minus 10z, z is just t, equals negative 4. And now you solve for x. So this is x plus 1 plus 3t minus 10t equals negative 4. I can subtract the 1 over and combine the like terms here, and I'll get x minus 7t equals 4. Negative 4 minus 1 is negative 5. And now add the 7t, and I get x equals negative 5 plus 7t. And these are your solutions. In other words, any ordered triple of the form negative 5 plus 7t, comma, 1 plus 3t, comma, t will solve. And I think you guys have done one of these in your homework from last week, a 3x3 with infinitely many solutions. How many could fit that whole problem on one page? If you did it. Probably not many. I know that if I just jumped in and tried to work that using elimination without a particular method to guide me, it would take a lot longer. So this rewriting your system as a matrix, then row reducing the matrix, is an incredibly powerful tool. It's what your computers do every time they solve a system for you, whether it's as a part of a computer graphics thing like in your GTX, or whether it's on your Bitcoin mining setup, or you'd be shocked the number of places where linear systems show up in computing. Yeah, I think we probably have time for one more, and we can make a point of looking at 25 from last week's homework. If you have no solutions, by the way, let me just say this really quickly, then instead of getting a line of all zeros like this, you would get like zeros here and a 1 here. Right? That would tell you that you have a contradiction. 0x plus 0y plus 0z equals 1 or 5. If you have all zeros here and something that's not 0 here, that means you have no solutions. Okay, so going to our homework. Can take a peek at number 25. Yeah, okay. So here you have a 4x4, even bigger system. We could do this by elimination, kind of jumping in blindly. Let's put it in matrix form. So I'll need a minute to write this down. This is x plus 0y plus z plus 2w equals 4. 0x plus y minus 2z plus 0w equals 1. X plus 2y minus z plus 0w equals 4, and then 2x plus y plus 3z minus 2w equals 0. All right, here's your system. And rather than trying to work in system land, I'm going to convert this to a 4x4 coefficient matrix augmented with this right-hand side. So it will be a 4x5 matrix. Coefficients are 1, 0, 1, 2, 1, 0, 1, 2, and then the right-hand side is 4. 0, 1, negative 2, 0, 0, 1, negative 2, 0, and then the right-hand side is 1. 1, 2, negative 1, 0, 1, 2, negative 1, 0, and then a right-hand side of 4. 2, 1, 3, negative 2, 2, 1, 3, negative 2, and then a right-hand side of 0. There is your augmented coefficient matrix for this system. I've already got a pivot here, and it's already 1. So now I need to clear out everything beneath. This guy is already a 0. So my first thing to attack is going to be this. I need to make this 1 here a 0. So my new row 3 will be negative row 1 plus old row 3. I'm going to subtract this from this. I might need more space than that. All right. So my first row is staying the same. 1, 0, 1, 2, 4. My second row is staying the same. 0, 1, negative 2, 0, 1. My fourth row I'm going to copy down because it's also not changing. 2, 1, 3, negative 2, 0. Third row is the one that is changing. Negative 1 times this plus this is 0. Negative 1 times this plus this is still 2. Negative 1 times this plus this is negative 2. Negative 1 times this plus this is negative 2. And negative 1 times this plus this is 0. There's my first row up. Now my next move is going to be to make this guy a 0. Just checking my work to make sure I didn't goof, because there's lots of room for little mistakes, but this looks good. So I need to get rid of this 2 now. I need to make him a 0. So I'm going to multiply row 1 by negative 2 and add it to row 4. So my new row 4 is going to be negative 2 copies of row 1 plus my old row 4. I'll make this nice and tall so I don't have to scrunch things. First copy down rows 1 through 3. They don't change. 1, 0, 1, 2, 4. 0, 1, negative 2, 0, 1. 0, 2, negative 2, negative 2, 0. And now we get to the row that changes, row 3. Negative 2 times this plus this is 0. Negative 2 times this plus this is 1. Negative 2 times this plus this is also 1, right? Negative 2 plus 3, that's 1. Negative 2 times this is negative 4. Negative 4 plus negative 2 is negative 6. Negative 2 times this is negative 8. Negative 8 plus 0 is negative 8. Now I'm happy with the first column. Got a 1 in the pivot and a 0 everywhere else. Move on to the second column. I need a 1 in the pivot. I have that. So now I need to kill everything beneath him. So I'm going to alter row 3. I need to make this a 0. So I'll multiply row 2 by negative 2 and add it to this. So my new row 3 is going to be negative 2 times old row 2 plus old row 3. Row 3 is the one that's changing. Let's copy everybody else down. 1, 0, 1, 2, 4. 0, 1, negative 2, 0, 1. We'll copy down row 4. 0, 1, 1, negative 6, negative 8. And now for row 3. Negative 2 times this plus this stays 0. Negative 2 times this plus this is now 0. Negative 2 times this is positive 4. Positive 4 plus negative 2 is positive 2. Negative 2 times this is 0. 0 plus negative 2 stays negative 2. Negative 2 times this is negative 2 plus 0 is negative 2. All right, we're getting there. Next, I need to make this a 0. Easiest way to do that is just take this row and subtract it from this row. So my new row 4 is going to be negative row 2 plus row 4. This is the last one I'll fit on this page. So row 4 is the one that's changing. We copy everybody else down. Now to do the job. Negative 1 times this plus this is 0. This guy stays 0. Negative 1 times 0 plus 0 is 0. Negative 1 times 1 plus 1 is 0. Negative 1 times this is positive 2. Positive 2 plus 1 is positive 3. Negative 1 times this is 0. 0 plus negative 6 is still negative 6. And negative 1 times this plus this, it's negative 1 plus negative 8. That looks like negative 9 to me. All right, we're getting there. Column 1 is done. Column 2 is done. Next, I need to make the pivot in column 3, this guy, a 1. To do that, I would divide through this whole row by 2. So my next row operation here, my new row 3 is going to be 1/2 of my old row 3. Everybody else stays the same. Dividing each of these by 2 gives me 1, negative 1, and negative 1. I almost wrote the right-hand side wrong. And then the fourth row stays the same. 0, 0, 3, -6, -9. Now that I have a pivot of 1 in column 3 here, I can use him to knock this out. So the row operation here, my new row 4 will be -3 times old row 3 plus old row 4. And then this will be my last necessary row op. Row 1 stays 1, 0, 1, 2, 4, 0, 1, -2, 0, 1, 0, 0, 1, -1, -1. And now -3 times this plus these guys all stay zeros. -3 times this plus this is 0. -3 times this is +3 plus this is -3. -3 times this is also +3. +3 plus -9 is -6. And then if you want to, you could divide through row 4 by 3 to get a 1 over there. Since, is that a -1 in row 3? Yes, this is a -1, yep. So since we are short on time, I'm not going to do this very last row operation where I divide through here to make this guy a 1. We can go ahead and go back to system form and solve. So this is equivalent to the system x plus 0y plus z plus 2w equals 4. 0x plus y minus 2z plus 0w equals 1. 0x plus 0y plus 1z minus 1w equals -1, and 0x plus 0y plus 0z minus 3w equals -6. And that last equation, equation 4, says -3w equals -6. And if you divide both sides by -3, you get that w is 2. Subbing in equation 3, so w is 2. We get z minus w equals -1. So z minus 2 equals -1, which means z has to be -1 plus 2, which is +1. Subbing these into equation 2, you have y minus 2z plus 0w equals 1, y minus 2 times 1 plus 0 times 2 equals 1. That's the same as just saying y minus 2 equals 1. So y equals 3. And now subbing all these into equation 1, we get x plus 0 times 3 plus 1 times 1 plus 2 times 2 equals 4. So x plus 4 plus 1 is 5 equals 4, which means x is -1. So there it is, the solution is the ordered 4-pole, -1, 3, 1, 2. Row reducing matrices by hand is not fun. I'll be the first person to admit it, and I won't make you do it any more than the bare minimum to learn how. But you do have to learn how. The cool shit comes next. The cool shit is when you start seeing how matrix multiplication, there is a way to multiply matrices, and it's not what you would think, relates to solving systems. It turns out that matrices, like there's an algebra, all the algebra is algebra of numbers. There's an algebra for matrices, a whole new system of algebra designed just for how matrices interact with other matrices. That algebra system will allow you to rewrite any system of equations like this, 10 by 10, 100 by 100 system, as a single equation, ax equals b. And then you just have to divide both sides by the matrix A. Dividing matrices turns out to be a complicated biscuit, but I will show you exactly what it means on Wednesday. Before we can actually do that, we're going to have to talk about how to multiply matrices, what matrix algebra is, all that shit. It's going to be a little complicated. The first step to getting there is learning how to row reduce. And I'll tell you that row reduction is an important part of dividing matrices. These things are equivalent to one another. So you can expect the skills you practice here will be important for the stuff that's coming up. That's where we're going. So next time I will show you guys how to rewrite a system of linear equations as a single matrix equation. And then we'll talk about what sort of things can be done to solve those matrix equations. It's going to be similar to this, but it'll be more fun, I promise. Any last minute questions before I let you guys go for the day? All right, I appreciate you guys hanging around. I will see you all on Wednesday.